Good evening, all of you. I am Mrs. Shraddha Kulkarni, working as an assistant professor in Department of Biotechnology, Siaghad College of Engineering, Pune, Maharashtra, India. And I have been working in this area from last 4 5 years. And the topic of today's presentation is production of hydrophobins from white rot fungus, Pleurotus austriatus. So, Dr. Kalpana Joshi and Dr. Sanjay Nene are my mentors. So today I will be discussing about introduction of the topic, hypothesis, objectives, materials and methods, result discussion, conclusion and references. So basically what are hydrophobins? Hydrophobins, they are self-assembling surface active proteins and they are of fungal origin basically, and they are very small proteins having 100 to 120 amino acids, and they have very less homology in the species and across the species, but they have a conserved domain of 8 cysteine residues, which is common in all the species. Based on that, they are classified into a new class of proteins called hydrophobins. Basically, the name suggests they are hydrophobic proteins, amphipathic in nature, having balance of hydrophilic and hydrophobic amino acids in them. They play a vital role in growth of the fungi, and in broader way they have been classified into class 1 and class 2. Class 1 are found in ascomycetes and basidiomycetes, but class 2 are only found in basidiomycetes. So, as they are amphipathic in nature and they are playing vital role in growth of the fungus, the major role they are playing is they are helping to reduce the surface tension of the media and helping the fungal hyphae to bridge that level and grow into the air. This property of hydrophobins to decrease the surface tension of the media, or the property of hydrophobins to alter the nature of the surfaces, is opening various applications for the protein. And nowadays people are trying the application of hydrophobins in medicine, like to make the antifoul utensils by layering the hydrophobins on its surface. Then in food and beverages, basically hydrophobins have been used for making the food foams with reduce the fat content of the foam by replacing fat with the hydrophobin. Then also hydrophobins have been used in purification of recombinant proteins as a tag protein. They have been used in increasing the bioavailability of the hydrophobic drugs. In biosensors, they have been used to immobilize the enzymes effectively, and also they can be used in various cosmetics. Looking at the various applications of hydrophobins, we should look into the wait yeah. So looking at various applications of hydrophobins, we decided to go for isolation of hydrophobins from grass cleared strain, generally regarded as safe strain, that is Pleurotus austriatus, the mushroom. When we studied common mushroom Pleurotus austriatus and its life cycle, we found around 44 genes of hydrophobins are getting expressed at each and every level of growth of hydrophobin, from monokaryotic stage to dikaryotic mycelium, then primordium phase, then young fruiting body formation, then mature fruiting body formation. And we observed that at each and every stage, there is an expression of different hydrophobins, which suggests that each and every protein, hydrophobin, has got a specific role in the growth cycle of Pleurotus austriatus. And we observe that VMH3 is the hydrophobin which is getting expressed everywhere at each and every stage of Pleurotus austriatus life cycle. So we went on producing the organism in laboratory, and we tried to isolate a few of the hydrophobins out of this 44 hydrophobin sets. So basically what are the attempts made for isolation and purification of hydrophobins from Pleurotus austriatus? VMH1, 2 and 3, POH1, 2 and 3 and FBH1 have been already isolated, and their molecular weight is determined, but only VMH2 is studied at some level to improve the yield, and they found it is around zero point 0.1 gram per liter of the yield of hydrophobin VMH3. VMH2 they have received by growing the organism in laboratory. But for VMH1, VMH3, POH1, 2, 3, and FBH1, there are no reported studies of attempts made for improving the yields. So, looking at the applications of hydrophobins and selection of the organism, we went on to study the levels of yields which are achieved by isolation of hydrophobin from this different fungi, and we found that there are very poor production of hydrophobins, and it is the bottleneck of industrial application of the protein. So production levels of native strains are on par with recombinant strains. So we decided to go for traditional methods of media optimization strategies which can improve the yield. And being a basidiomycete strain, we also tried to grow in solid state fermentation, which is a natural habitat for any fungus to grow. Reported studies suggested that the substrates like wheat bran, cassava bagasse, sugarcane bagasse, and different waste oil cakes are there available for growth of Pleurotus austriatus. We decided to go for waste oil cakes, considering the hydrophobic nature of the substrate, which can support more growth of hydrophobin and yield can be improved. So this was our overall strategy. We selected the strain, ordered it from National Collection of Industrial Microorganisms provided by NCL Pune. Then we cultivated in different liquid media. We purified the hydrophobins. We studied its biosurfactant properties to confirm the nature of the protein. Then we characterized it, and then we produced it in best selected liquid media and also produced it on solid state fermentation support. So these were our objectives: production of hydrophobins from P. austriatus using different liquid media in submerged liquid fermentation, and study of solid state fermentation for enhancement of production levels from Pleurotus austriatus. So this was the overall strategy. We grown it in PDA plates. Then we inoculated the mycelia in different liquid media. We collected the fermentation broth, and mycelia was treated for purification of hydrophobins. And then we carried out one factor at a time method to improve the production level to select the best medium. In case of SSF, we have grown the mycelia and inoculated it on selected substrate, and moisture content was maintained at 75%, and the supernatant was collected by treating the substrate grown with the mycelia, and then we purified the hydrophobins of it. So these are the media composition selected for screening experiment: PDBY, yeast extract, glucose malt extract with pH 5.5 IMG media, then basil culture medium which contained peptone, yeast extract, ammonium sulfate, potassium diiodine phosphate, magnesium sulfate, glucose, and SC minimal media. SC minimal media is Schizophilum commune, one of the mushroom minimal media. And using this media, people have isolated hydrophobin SC3 from SC strain Schizophilum commune. So we decided to go for this media, as the role of hydrophobin VMH3 in Pleurotus austriatus is similar like the SC3, which is expressed by Schizophilum commune. Then for fermentation broth, after growth of 10 days, we collected the fermentation broth and followed the bubbling using the varying blender, and collected the foam, centrifuged it to pellet out the hydrophobins. These hydrophobins are now in aggregated form. To make them monomer, we treated it with 100% TFA, sonicated for 30 minutes, and then the protein concentration was estimated. For mycelia, the process was little lengthier. Basically, hydrophobins are insoluble in SDS. So we treated the mycelia with hot SDS, 2% hot SDS for 4 to 5 times, and washed the mycelium continuously with water to remove all the hydrophilic proteins. Then whatever remaining mycelia were there, it was lyophilized and treated with TFA to extract out the rodlet layer of hydrophobins. Hydrophobins are forming rodlet layer in the cell wall of fungi. So that rodlet layer was removed, and also it was dissociated into monomers using TFA. Instead of TFA, we can go for formic acid and performic acid, where formic acid will extract out the rodlet layer and performic acid will convert it into monomer. But trifluoroacetic acid is playing both the roles. So we replace TFA with formic acid and performic acid. And then we followed a heat shock treatment which is a less costly treatment to isolate the hydrophobins and get it in a more pure form. So after purifying the protein, we tried to study its surfactant properties to categorize the protein into the class of hydrophobins. We tried to get the half-life time of the foam which is produced by hydrophobins, and we compared it with the standard surfactant SDS, and the concentration was selected 0.1%, and we found that the half-life time of SDS was 80 minutes, and for our protein it was 70 minutes, so it was comparable. Then we tried emulsification of the different cooking oils using hydrophobins, and we found with sunflower oil it has given the maximum 80% of the emulsification index. By performing these preliminary studies, we went on to characterize the molecular weight of the protein. We performed SDS page, and we found two pure bands of 10 kilodalton and 17 kilodalton on SDS page. The same sample was sent for purification using HPLC, and we got a characteristic peak in between 30 to 40% of the acetonitrile gradient. The gradient process of HPLC was followed for the same, and this peak is matching with various hydrophobins previously isolated and purified using HPLC. Being a amphipathic protein, it always gets separated at 30 to 50% of the acetonitrile concentration gradient. To further study the protein, we followed Orbitrap HRLCMSMS, and we found the protein which we have isolated is VMH3. So, as we got a new protein which is not isolated before our work, and the data is not available in the literature, we studied its amphipathic nature. To study its amphipathic nature, we applied this protein onto Teflon, and we just checked the water contact angle change in Teflon. Basically, Teflon is hydrophobic in a nature, and when water is coated into bare Teflon, its water contact angle is typically 134 degree. By application of VMH3, this angle was reduced up to 102 degree when it was coated with VMH3 isolated using from mycelia, and when it was coated from fermentation broth, the angle was decreased by up to 90 degree. This decrease in angle suggests the decrease in hydrophobicity of Teflon, and here we studied the alteration of the surface, which confirms the amphipathic nature of our protein. Then next to that, we went on to media optimization, which is submerged liquid fermentation. And we selected, as I have previously shown in my slide, uh, we selected different media, PDBY, SC minimal media, BCM, and YMG. And we got maximum production in YMG. From mycelia, it was around 15 milligram per gram of mycelia. And for foam, that is from fermentation broth, it was around 38 milligram per liter. Then it was also tried using SSF and cassava bagasse and sorry, not cassava bagasse, it is coconut oil cakes and sesame oil cakes, which we tried for production of hydrophobins using SSF. And here the production levels were definitely high as compared to other media used, liquid media used, but less than the YMG. So we found that in submerged liquid fermentation using YMG, we got maximum production of hydrophobins, and we confirmed the presence of the proteins in SSF by performing SDS page. So we further decided to go on optimizing the parameters for production of hydrophobins in liquid fermentation, and the way which we used was the traditional method of OFAT, one factor at a time. Here we have optimized the C source, carbon source, by replacing glucose with galactose, sucrose, fructose, xylose, cellulose, starch. And we found that glucose is the most suitable sugar or a carbon source for production of hydrophobin, which have given the maximum yield. Then we went on to optimizing the pH 4, 5.5, 7, and 9, and we found that at pH 5 the yield was optimum. We also tried different temperatures, and actually at 35 degrees Celsius, there is a slight increase in production of hydrophobins, about 16 milligram per gram. So these are the conclusions of our work. We have selected a new strain of Pleurotus austriatus and explored for isolation of hydrophobins. Biosurfactant nature of a culture broth encouraged for extraction of hydrophobins, which has shown good foam stability and emulsification properties. HYD-LP was identified as VMH3 by Orbitrap LC-MSMS, and it is reported first time that VMH3 is isolated and identified using LC-MSMS. Different liquid media were screened for production of hydrophobins. That this type of work is never done for optimizing the production levels of HYD. SSF helped to reduce the days of growth of mycelia. Yes, we have got a good growth in 5 to 7 days in comparison to SLF, where it takes 10 to 13 days, and resulted in the yield of hydrophobin of around 3.85 milligram per gram. OFAT approach was used to optimize the yield, and we got 14.39 milligram per gram of yield of hydrophobin per dry weight of mycelia. Hydrophobic nature of these proteins was reconfirmed by reduction in water contact angle measurement on Teflon surface. These are my references. Thank you.